Hi, my name is Ian Fogarty, and I'd like to talk to you a little bit about organic chemistry and hydrocarbons and alkanes today. This is the introductory lecture. Organic chemistry is the chemical study of anything that was or is currently alive, which really means the area is quite wide open. Take all the molecules known to man and put them in one great big book. The vast majority of them would be organic. The nice thing is it uses a limited number of atoms. There's a whole bunch of elements on the periodic table, and out of those, we only focus on a few short pieces, C, N, O, H, and a little bit of S and P for spice in there, a few little halides. But really, the vast majority is going to be carbon, nitrogen, oxygen, hydrogen. If you can work with those four elements, you've got a bunch of it nailed down, which is really interesting considering that there's so many elements on the periodic table that you can talk about most molecules in the world if you just focus on these four atoms. It's important for us to investigate Lewis dot diagrams a little bit, a review from Chem 11. You have to remember that it's the outer electrons in the valence shell that really determine most of the reactivity of the element. For hydrogen, hydrogen has one electron in its outer shell. And carbon has four, so we often write carbon something like this. Four electrons in its outer shell. Whereas nitrogen has a lone pair, two of them side by side. And then three solos, 5 electrons in its outer shell. Oxygen has 2 lone pairs most of the time. Over. And I've included fluorine just to be complete. And if you remember way back, Bohr used to talk about magic numbers of 2, 8, and 8, and the idea that every element wants to have a full valence shell. And for any element in the first 3 rows of the periodic table, that's a 2 or an 8 or an 8. And so this hydrogen has 1 electron in its outer shell. It would like to have 2, so it's going to try and find another electron somewhere. And so what might happen is if it could find another hydrogen, it would have its 1 electron there, another hydrogen with its electron there. They could each donate 1 electron and end up with something like that. And so now this hydrogen can look at those 2 electrons, that hydrogen can look at those 2 electrons, and you end up with a bond, 2 electrons in our bond. So when you make a bond, 1 electron usually comes from one element, another electron comes from another element to form my bond. So hydrogen wants to make 1 bond with one other thing, so we can get 1 electron extra to make a grand total of 2. Carbon, on the other hand, has 4 electrons in its outer shell. It would like to have 8. So if it's going to get a total of 8, it needs 4 extra electrons. If those 4 extra electrons are coming from 4 other elements, it means it's going to make 4 bonds. So hydrogen wants 1 bond to complete its shell. Carbon needs 4 bonds to complete its shell. Nitrogen has 5 already. It's looking for 8, so it needs to make 3 bonds with something if it can. Oxygen would like to make 2 bonds. And fluorine has 7 already, just needs 1 more, so it wants to make 1 bond. So I'd like to look at making some carbon-carbon and some carbon-hydrogen bonds for a second. So if we go and we make our Lewis dot diagrams here ever so quickly. So there my carbons each have their 4 electrons in their outer shell, and so we could make a bond between these guys right here. We could make a bond between those guys right there, and they could share those ones. And that would be great. But the problem is this carbon would now have 1, 2, 3, 4 plus the extra one for that he's borrowing from him. So 5, it needs to have 3 more. So how's that going to look? Well, fortunately, we have a hydrogen with a 1 electron. So they could donate an electron, and that one could pair up to form a bond. And that gets us a little closer, but we still have a ways to go. And so we could have another hydrogen with its electron donate 2. And we should start seeing a pattern here. And now we can see that the carbon, the center carbon, has 2 electrons that it's sharing here, 2 more here, 2 more here, and 2 more here. So 2, 4, 6, 8. Its full outer shell is full. This carbon also has 2, 4, 6, 8 that it's sharing. So its valence shell is full and happy. Each hydrogen has 2, 2, 2, 2, 2, and 2. And our valence shells of 2 and 8 are all full. Bohr would be happy with this. And there's our molecule. Let's take a carbon and create our very simplest organic molecule. It is prevalent and all over the place. It is a major contributor to greenhouse gases. It's about 25 times more potent contributing to greenhouse than carbon dioxide. So our Lewis dot diagrams look like this. So those could get together, those could get together, those could get together, and those could get together, and then we would end up with... So we end up with our very simplest organic molecule, and this is methane. M-E-T-H-A-N-E, methane.